So it's for me a great pleasure to be with you. And I wanted to share some thoughts on the links between control theory and machine learning. There will be a second talk by Vladimir on similar topics. I think he will get much deeper than I into the machine learning paradigms. So my talk will be more general. My aim is to somehow emphasize that there are plenty of bridges, plenty of links between these two disciplines. Actually, machine learning, mainly developed by computer scientists, is very much grounded on the foundational, say, ideas and methods of other disciplines in applied mathematics, like control, optimization, and the calculus of variation that, as you know, oftentimes are hard to distinguish, right? So we are used to say that, these are different areas, different disciplines, but oftentimes are kind of different perspectives, different, say, formulations of the same problems, right? So maybe there is a way of turning off all the micros because there is a lot of background noise. Maybe the manager of this can just simply turn off all the micros. Yeah, I think it's good now. Thank you. Yeah. Okay, so and then, as you know, mathematics is very broad. Applied mathematics and mathematical sciences are very broad. And things get even broader when you talk about machine learning, which plenty of, say, interactions with computer science, engineering. The same happens in control theory, where you can talk about, automatic control, about cybernetics, about, actually in Poland, there is this celebrated journal, Control and Cybernetics, right? Following the term coined by Norbert Wiener, control engineering. So it's very hard to put the boundaries, or how far we can go on the landscape of mathematical and in general sciences when we start talking about these topics. But then, assuming that there is an area of, say, mathematical sciences and engineering that we can describe with some contours, if there was a country, whose name were control, my claim is that machine learning is really a neighboring country with a common, right, a quite, say, large interface, a large border, right? And of course, the way you can discover this is like, you go to the Amazonia. Amazonia is so huge, there are many ways of exploring Amazonia, right? You can start from, one corner or the other, right? Maybe as a tourist, you start from Manaus in the North Brazil, but there are many other ways of getting to Amazonia from different countries. So this is exactly the same here. So control and machine learning are two neighboring valleys of applied mathematics and mathematical sciences. They are very strongly interconnected. There are many paths, there are many tunnels. I will just tell you about some of them, okay? So, and of course, I'm doing it from my own perspective, from, the kind of topics I know the better. I hope that by doing this, even for those that maybe don't have exactly the same expertise as I do, and you have a different perspective to this broad area of dynamical systems, networks, neural networks, control, dynamics, and so on. I hope by this talk, you will yourself, in your own language, in your own territory, scientific, say, area of expertise, you will be able to recognize at least some of these, say, signals of such a strong link, right? So one of the maybe most classical results in control theory or cybernetics, as Norbert Wiener defined, right? He said, is the science of control and communication in animals and machines. And you see that, you know, already in this very definition of cybernetics, right? Animals and machines that will be able to replicate the work of humans so that humans are free to do other tasks, right? So then, I don't know, you can talk to the computer and the computer will write the letter. In this way, you don't need a person, like in the old times, that will be, while one is talking, the other one is taking notes very fast, right? And suffering a lot to be able to reproduce the speech. Now the machine does it. So one person at least is free, right? So machines to free animals, to free humans by mimic what humans are doing. This was the definition of Norbert Wiener of cybernetics, of control sciences, of automatic control. So you see already that in this very definition of cybernetics, you see the strong link with machine learning, right? So this is precisely what we would like to do, right? So we want, I don't know, we want to use some automatic translator of text like DeepL based on deep, say, neural networks that will be able to translate a text from English to Polish automatically without requiring the hours of dedication from a, say, human translator. Okay, very good. So now, how one can formulate from a mathematical perspective this very idea of Norbert Wiener that, you know, machines should do the work of humans. So I like this result by Norbert Rudolf Kalman back in the 50s. He was not the only one to do this. So I mean, there were many other people like Lee from Lee brackets, you know, Lyapunov, Lassalle, I mean, doing things that were related. So I'm not claiming that this was 100% Kalman, but it's certainly written in his, say, pioneering papers on control. And it was very, say, a great contribution that the problem was already formulated very precisely. So Kalman said, we are considering a finite dimensional linear dynamical system driven by a matrix A, right? So here, this is a finite dimensional system. It could be the space discretization of a PDE, for instance, right? But it could be also some rough modeling for, say, a social network, right? So on the state X, with n, capital N components, x1, xn, we are recording the opinion of the n persons in this, say, social network or WhatsApp group, right? Okay. A is the matrix of interaction among the different individuals. Not all of them interact with all others with the same intensity, right? We talk and we see and we take into consideration the opinion of some friends or family members, you know, more seriously than from others, right? So there is a free dynamics of the system, right? And then, but then we have the opportunity to control this system. It could be also, you know, temperature in the different rooms in the faculty of sciences where you are working, right? So there are, like, I don't know, 25 rooms, X1, X2, Xn will be the average temperature in each of these rooms. These rooms are interconnected. There are doors and corridors. This will be modeled by A, and heat is diffusing and circulating, right, in this building. But then we are regulating temperature, right, through the injection of cool or hot air, or we could be also influencing, you know, the dynamics of this social network by inputting information, relevant information, right? So there could be, oh, there is a new war, or, you know, one of the world leaders passed away last night, or there was some terrorist attack in some town, or there was an earthquake here or a tsunami there, and this will very much influence, right? So how people feel, what people believe on specific topics. But then the point that Kalman was doing was that, okay, so this system typically will have a very high dimension, and the number of components of the system can be very high. And still, you might have only just a few parameters, M, to control the system. So, and the question is, can you control a very complicated system with many components N if you are only allowed to regulate, you know, like 2 or 3 actuators when M is much smaller than N? So in this case, there is not, you cannot apply the logic, and you don't want to apply the logic of linear algebra, saying, okay, you want to control n components, you need n controls. I mean, this will be unaffordable in practice. You want really to control a very complicated system, right? Just by a few, say, actuators, right? That you can really regulate, take decisions on. The question is whether you can. Now, later, whether you are able to find the right strategy to control that system, this is something else. So this is why not every one of us can be a Formula One driver, right? So we have a driving permit, but we cannot be Formula One champions. Yes, in principle you can, or you can be pilot of an airplane, but you cannot, you know, guide an airplane with the driving permit of a car, simply because this is much more complicated. And you need a lot of training to learn how to control a system with many more dimensions just by using basically your two hands, right? So, you know, the bigger is the gap between the number of controls m and the dimension of the system n, the more difficult the exercise will be. But still, the question that Kalman was asking was, but can one or not? Is there a way, is there a control, even very difficult to implement and maybe inaccessible for many of us, but can I at least guarantee whether such a control exists? And the condition he gave was, this can be done if and only if this rank condition is fulfilled. And the only thing you have to do, right, to check this rank condition is to just superpose the matrix B, AB up to the power n minus 1B and check whether this is a full rank. So basically, right, what this rank condition is telling you, and the fact that the rank is n, is filling the whole space, the n-dimensional Euclidean space where trajectories is living, what this Kalman rank condition is telling you is that if the rank is full, then by combining in a smart manner all the controls you have at your disposal, which are just m, but if you make a clever combination of all these m controls, you can, you know, you can guide, you know, the trajectory in any possible directions of the Euclidean space, meaning that you can, you know, eventually drive the trajectory from any initial point to any final point. In case this rank will be less than n, will be like, for instance, n minus 1, then it will mean that there is one direction in the Euclidean space in which the trajectory cannot be controlled. So this is, for instance, the example of the car. So a car is controllable on the plane. We can drive a car on the plane. I mean, if there are no obstacles, if we are in an open field, we can drive the car from any point to another point. But if you ask me, is the car controllable in space? Then I can tell you no, because I cannot, you know, move the car on the vertical direction, right? So the car is controllable in R2, but is not controllable in R3. If I will check the Kalman rank condition for the car, I will get 2, but I will not get 3. Okay. So actually, in this, you know, classical textbook of Eduardo Sontag that you can download from the Springer webpage, he presents the analysis of Nelson's car. It's a very simple car in which you simply, for instance, think on what are the minimal number of parameters I need to describe a car. I need 2 parameters for the center of gravity, 1 for the main axis of the car, and 1 for the angle of the wheels with respect to the main axis of the car. 4 parameters, but I only have 2 controls, so the gear and the acceleration. Now, with 2 controls, we can control a system which is now evolving actually in 4 space dimensions, right? And in order to do that, you need to deal with this Kalman rank condition. As I said, even when the system is controllable, it doesn't mean it's going to be easy to control. So this is, you see this articulated track, right? So in this case, the exercise was, the track was parked here, and the track had to move to this other position here, but without leaving, you know, the space of this rectangle, the parking, you know, area, right? And you see what the optimal trajectory is. You have to move forward and then backward, and you see that you have to develop this kind of sinusoidal say, trajectory to be able not only to control, of course, the main body of the car, of the truck, but also those that are attached, adjacent to it. If you want to do that and really finish in this, rectilinear equilibrium configuration for the truck, right? You have to really develop such a strategy. So this is a typical example in which you are increasing the dimension of the car, right? Because now, the alignment of these three bodies is also extra parameters of the system, but still you can. You see, however, that the fact that you can doesn't mean that it's going to be easy, and therefore, very often you have to develop sophisticated, say, computational methods in order to find optimal trajectories. And, there is a huge literature in control theory about, whether nonlinear systems are controllable or not. The Kalman rank condition is just for the simplest linear autonomous problem. You can go into the infinite dimensional setting, PDEs, you can do stochastic systems. And then, of course, there is a lot about how, to compute controls and how, you can achieve this or not, depending on the constraints that you are allowed to fulfill and so on, okay? Of course, there are some other, say, magical control strategies, right? That will be fantastic. It will be much easier to do it like this, but this is definitely not an accessible control, right? So precisely, this video, which is a joke, but still is showing us that, often it will be, delicious, very helpful to be able to just push the car, on a given rectilinear direction. But unfortunately, we cannot do that because we can only regulate gear and acceleration, and we have to do many, twistings and many efforts, smart combinations of these two motions in order to be able to perform this action of parking a car. Okay, that's little introduction to control theory. Now, when you are dealing with dynamical systems so far, I didn't see anything and didn't say anything about the time horizon. Actually, for linear control systems, the Kalman rank condition you see is just purely algebraic. It's about the rank of A and B. It doesn't say anything about the time horizon. Then when the rank is full, the system is always controllable. Of course, when you make the control time horizon very narrow, of course, you will have to, control very strong. This is like if you are going from one town to another, right? Like Erlangen, Nürnberg is like 20 kilometers, typically will be 15 minutes. If you tell me that I have to go there in 2 minutes, well, I have to drive 500 kilometers per hour. I mean, if you do it you want to do it in very short time intervals, you need a lot of intensity. If you are allowed to do it in a very long time, if you give me, say, 4 hours, I can walk to Nürnberg. It's 20 kilometers. I can walk 20 kilometers maybe in 4 hours, and I don't need to go that fast, right? I don't even need a bike or a car. If you give me 1 hour, I can do it by bike. Okay, but if you give me 10 minutes, I need a supercar. Okay, but still, you can always do it. Now, there was, however, this fundamental and seminal, say, contribution by von Neumann. Von Neumann was thinking in terms of, economic planning. And he made the following observation. When you are thinking on long time horizons, very often optimal trajectories are most of the time steady state. And this was then later further developed by Paul Samuelson, who got the Nobel Prize in economics, right, for his theory of Turnpike. And he summarized, the meaning of Turnpike in this sentence, which basically means something we all know. If you are going, say, from Erlangen to, I don't know, Krakow, say, in Poland, okay, I don't know how many kilometers there are. There are a few hundred kilometers, okay? When I asked to Google, please give me the instructions, tell me what is the best path to go from Erlangen to Krakow, Google will answer. Google doesn't need to know whether in Erlangen I am departing from home or from office. And Google doesn't need to know whether in Krakow I'm going to the university or I'm going to the hotel. Why? because basically the answer is independent of the precise point of departure and the precise point of arrival. This is because, you know, the optimal trajectories, they always look like this. It means from home, I will quickly drive to the optimal highway. Then I will take the Turnpike, the highway that is kind of static, you know, constant velocity, 120 kilometers per hour. I drive along this highway until I am getting close to Krakow. And then when I am getting close to Krakow, I will again have to adapt my final arc to my precise destination. Of course, the initial and the final arc will change depending on where I am departing from and where I am arriving to. So this initial arc will differ depending on whether I am departing from office or from home. And this final arc will again depend on whether I am arriving in university or in the hotel. But in the meantime, 90% of the time or 99% of the time, I will always be in the Turnpike, right? This was the fundamental contribution of von Neumann, right? In long time horizons, steady state strategies are nearly optimal. This is why you see, for instance, if you have a chronic disease, you know, the doctor will tell you, okay, take 1 pill per day and come back 6 months from now, and we will do another test, blood test, for instance. Or, you know, the Bank of Europe is setting up, right, the, you know, the interest rate for loans for 6 months. They could do it every day, changing the interest rate every day. But according to the theory of Turnpike, this is really not necessary. You can, if you choose the optimal steady state interest rate for 6 months, this will be good enough. And then, of course, after 6 months, you will have to revisit it because there are some deviations of the, you know, global dynamics of the planet. Things can happen. There can be a war or an earthquake, and this a new unexpected virus or crisis here and there, and this forces you to adjust, right? So then you see already 2 ideas. The first idea is controllability. I mean, this is something that we are used to. We know how to drive bikes or cars, right? This idea that you have to somehow do zigzagging, combining different controls in a smart manner in order to generate motions that apparently are impossible in order to be able to manipulate and to drive engines in high dimensional spaces. And there is also this idea that, you know, of course, not only the size of the control depends on the time horizon, but also the nature of the controls that you will need to use also depends on the time horizon. If you have to work on a very short time interval, the controls you will use will be like Dirac delta. This is like a defibrillator, right? So if someone has a heart attack, I mean, the action has to be instantaneous and has to be a, you know, a very intense, like Dirac shock action, right? So short time intervals, Dirac control, long time intervals. Rather, keep in mind that you are more in the context of Turnpike, where controls tend to be, say, steady, right? And that's something that is important. Now, in the PD theory, Glowacki and Lyons in the late 80s, they were doing simulations for the control of heat-like equations, and they discovered these, say, oscillatory patterns. And they said, well, why these oscillatory patterns for control of heat? The heat equation is going down nicely. It's a diffusion model. It's a linear, say, infinite dimensional system that is exponentially stable. Why, if I have to control an exponentially stable dynamics, the control will have, you know, this tendency to be so much concentrated at the end and oscillating in such a high frequency capricious manner, right? So there are also paradoxes. At that time, people didn't know. I mean, is this because the Turnpike principle doesn't work for partial differential equations? Is maybe due to the fact that this is an infinite dimensional system and that the theory that, you know, von Neumann and Samuelson and the others developed was mainly oriented to finite dimensional system? What's going on, right? And then we look at this more carefully, and this was our first contribution in this topic with Alessio Porretta from Rome. We said, okay, let's check. Let's go back to the problem of Glowinski and Lyons, just regulating temperature in a cavity omega by controlling acting on a small omega. Let's assume we are just doing the standard thing. I want to drive temperature in the room to a given chosen ideal temperature, say 21 degrees. How high do you need to play with the control F in order to drive temperature to 21 degrees? So the way you will do it in, say, computational practice, in an application, of course, you can deal with many very sophisticated issues related to controllability, but the way you actually do it in practical applications will rather be this. We'll say, okay, let me just minimize. I use some finite element code for solving the heat equation. Let me then just minimize a functional like this with two criteria. In this criteria, of course, I'm pushing the solution to get close to the desired temperature, right? Because I'm minimizing this distance square. So to minimize this distance square, the solution at the final time has to get close to the target. But of course, I will also penalize the control. I don't want the control to be too large, because otherwise this will burn an amount of energy that I'm not ready to pay such an expensive bill at the end of the month to the electric company. So I have also to put bounds on the control, right? If you do this, and you apply Pontryagin maximum principle, which is a generalization, as you know, of say, Lagrange multipliers, right? In this very context, what you observe is that the optimal solution Y and the optimal control, right? The optimal control is just given, F is just given by the adjoint state P, where the adjoint state P in this case fulfills the adjoint heat equation, right? With a minus sign here. But because of the very nature of this functional, this P is totally independent of the Y. And now if you think a little bit on this picture, you understand why this picture was correct. They were doing nothing wrong. They were just observing numerically very precisely what the theory anticipates, because the theory says the control is given by the adjoint state, and the adjoint state is a solution of this heat equation. Now, what is this heat equation? This is actually the backwards heat equation. So this heat equation is doing, in the backward sense of time, what you see here going from time 1 to 0, is doing in the backward sense of time exactly what the heat equation will do in the forward sense of time, right? And what does the heat equation do in the forward sense of time? The energy has the tendency to go down. And of course, if you start with an initial datum which has, say, oscillating sign, this will be done through oscillations. So what you see in this picture is just the reverse presentation of the standard trajectory of the heat equation in the forward sense, just recorded in the backward sense. So this explains everything. Okay, so then the conclusion was, then there is no Turnpike for PDEs, for the heat equation? No, there is something else you can do. Actually, and this is something very important also in the context of machine learning, you have a lot of freedom as a control scientist. You can say, I want to control the heat equation, but I can also change the criteria for control. I mean, I propose you to modify slightly your choice of the control by now making a compromise, not on the first two criteria, distance to the target and size of the control, but also the size of the trajectory as well. And this is also very natural, right? Because when you are driving, you are not only aiming to get to the target and not using too much gasoline because it's quite expensive nowadays, but you also try to avoid too high oscillations. So you penalize somehow the amplitude of the deformation along the trajectory, right? When you do this, which is very natural, the Pontryagin maximum principle tells you, now the optimality system changes. And the optimality system changes because I added this term here. There is a y in the equation of P. So this is a system that people have the tendency to avoid because it's much harder to understand. You see, there is a P on the equation for y, and there is a y for the equation of P. Now you cannot uncouple this system as I did it before. But it is because of this coupling that the spectrum of this system is split into the stable manifold corresponding to the eigenvalues with negative real part, and the unstable manifold corresponding to the eigenvalues with positive real part. And this is what explains precisely the Turnpike. This is the stable manifold, eigenvalues with negative real part that go down to the Turnpike, the optimal steady state, to later quit along the unstable, say, manifold. Okay, that was about control. Now, machine learning. In principle, it's a different field. Yet, I claim, is really very, very close. And this can be seen very nicely in a number of aspects of machine learning. There are others that probably are farther away of this kind of dynamic control methodologies, but this one is very close. So this problem is maybe the simplest one in machine learning is supervised learning. It's just classification, right? So now, I didn't say before how all this is, related to the initial goal of Wiener of linking machines to animals and humans so that machines can do the work of humans. Well, if you implement this methodology well, in the end, you end up with a thermostat at home that is able to regulate the temperature in your office or in your living room, and you don't need to pay attention constantly whether it's too hot and therefore you have to turn off the heating, or whether it's getting too chilly and then you have to turn it on again. The thermostat is doing the work with you, for you, right? So what is a machine? A machine for a mathematician is a model, is a good understanding of the control of this model, right? And it's an algorithm, right? So then the algorithm is put in the computer, and this is implemented through, the technology of sensors and actuators into a real machine. But for us, at the level we are, for us, machine is just a mathematical algorithm, right? And this is what we did. Now, when you get into the world of data, one of the main and primary tasks is classification. We want to classify things, right? We need to classify things. In the library, the librarian needs to classify books according to the AMS classification, and then books of algebra and analysis and topology have to be, well ordered so that people can easily access to them, right? So that helps. If you are looking for a textbook in, in linear algebra, you know to which section of the library you have to go, okay? Or you are looking for a specific journal, you know where it is, right? And all issues of this journal, all volumes are all gathered chronologically, right? So classification is very important. Hospitals need also to classify patients into those that are very healthy and they don't really need much attention, and those that are on a high risk, okay? Very good. In the COVID age, we needed to classify people into those that were, vaccinated or not vaccinated, for instance, okay? So now we need a machine. And what is a machine? A machine for us is a function. It's a function that is able to classify successfully, something we can do easily. If you give me plastic bottles, I can put them in the plastic yellow basket. If you give me glass bottles, I can check it's glass, I can put them in the green. If you give me paper objects, I put them in the blue. If you give me bio-organic things, I can put them on the gray or on the brown, right? I can do that myself, yes. The question is to build a machine that will do that. And how do I do it? I do it through supervised learning. I have to train. Training means I have to build a machine that understands how to do it successfully with all these many items. Because if the machine does successfully the exercise with those many items, right, then very likely when there will be a new item coming, the machine will put the item by analogy with the previous ones in the corresponding basket. This is the same as when you learn how to drive. I mean, maybe you take 20 lessons. I mean, you just take 20 lessons for driving, and then you will be driving hundreds or thousands of hours along your life. But if these lessons are good enough, then you are trained to face more or less all the possible scenarios that can appear, right, when you are driving. For instance, rain, reduced velocity, red light, stop, and so on. Okay? Very elementary things that you learn and you implement efficiently, right? And then you are ready to start driving and, you know, being exposed to unexpected events. The same, right? So here we want a function that is able to take one of these items. What is an item? I take a photo. A photo is, I don't know, 27 times 27 pixels, is a point in a Euclidean space. So after all, every item is just a point in a Euclidean space of a high dimension. And then the basket is just one specific point in that space, right? So we want, you know, all the yellow ones go to the yellow reservoir, all the green ones go to the green reservoir, and so on. We just need a function doing this. How can this be formulated in a control setting? Well, this can be done using nonlinear dynamical systems, right, that are driven by nonlinearities that play a seminal role in the theory of neural networks, right? So you see here, our perspective is different to the classical one in, say, control theory. Normally, when you are dealing with control theory, we say, oh, I need to regulate temperature. So I go to the book in continuum mechanics, and the book says, oh, for temperature is the heat equation. Then I need to control the heat equation. And for that, I need to open the book and I see, oh, heat equation is parabolic, and then parabolic equations have these properties. Solutions are smooth, but it's time irreversible, and the numerics has to be, you know, done carefully according to this, and so on. So here is totally different. Nobody gave me the PDE. Nobody gave me the ODE. Nobody told me I should use ODEs or PDEs. The only thing I need is just a machine. And this machine, according to the classical theorem of Cybenko of, say, universal approximation, it can be built as a function in which you are simply making linear combinations of, say, these sigmoidal functions, which, you know, can be simply a sigmoidal function, can be just, you know, an arc tangent function whose limits at -infinity are 0 and 1, or the ReLU function, the so-called rectified linear unit, which is this very elementary function that is 0 to the left and linear to the right. So any of them will do it, right? And then Cybenko said, this was a theorem in approximation theory, every function can be approximated by functions this way. This was a density result. Polynomials are dense, Fourier series are dense. These neural networks built by Cybenko are dense as well. Now, if they are dense and this sigma there is so relevant, right? The goal, whatever it is, when we are trying to build a function f that is able to classify all these items, which is a map from RD, the space of images, into, say, Rn, the space of, you know, the baskets, you know, not necessarily the same, right? And n, capital N, is the number of items in the collection, right? So in this case, something like 8 times 432. If this is the task to be done, according to Cybenko, you can guarantee this can be achieved with an epsilon error as small as you wish because of the density of the universal approximation theorem, just by using, you know, proper coefficients. And this is what led to the idea that what if we try to do it according to a dynamical system? After all, this is very natural. This is what we do, right? So I take the bottle, right? I take the bottle of plastic. I take my iPhone, right? So I take my iPhone. I say, oh, this is what? This is glass, okay? And then it goes to the green basket. So I am defining a dynamical system in which I am taking this object and I am putting it in the corresponding basket. But then I take a glass and I say, oh, this is made of, I don't know, it could be a plastic glass. This is ceramic, but it could be a plastic glass. Or according, if it is plastic, I will, you know, transport it along this dynamical system and I will put it in the corresponding yellow basket. So you think from this perspective, how humans, we classify objects in a dynamic manner. You get to the, you know, to the room of your kids and you see all, you know, all toys, you know, randomly distributed along the room, and then you decide to, you know, to put some order on them. You will say, oh, you know, all the balls will go to this corner, all the tracks will go to this other corner, all the pieces of the puzzle will go to this other corner, and then again, you develop some kind of dynamic strategy in which you are picking up one and then transporting it to the corresponding destination. But now you see the main difference of classical control theory with control theory for supervised learning is that this time you want a dynamical system that is able to control all these trajectories simultaneously. So the machine that we are aiming to build has to be done in such a way that whenever you turn on this machine might be able to really distinguish all plastic objects and put them into the yellow trash, and all the glass items and put them into the, say, green, basket. Meaning that the same dynamical system, the same machine, has to be able to control all trajectories simultaneously. And this is when, we try to do it from scratch. We say, now there is no mechanics. I know dynamical systems, I know control theory of dynamical system, but now I am allowed to build my dynamical system because this is the machine I am trying to build for classifying items. And I decide to choose this machine as being such a dynamical system, right? In which now the parameters of Cybenko become time-dependent controls. And my claim is that the result by Cybenko that was proved in this static context, no time, just an approximation theory result, can be turned into a uniform or universal, say, ensemble controllability for this kind of dynamical system. So my references are there. This is a work that we have been doing in our team for the last, say, 2.5 years or so. And as you will see, the main ideas of the proof are the same as for the Rubik cube. So what do you do when you are solving the Rubik cube? When you are solving the Rubik cube, you are doing very similar, because you want to, introduce motion on all the items or most of the items of this Rubik cube, and you want to bring all, reds to one face, all greens to one face, all blues to a different face. So you are searching for perfect classification. Now, how do you do that? You do it in a finite number of motions, and in each of these motions, what you are doing is you are holding the Rubik cube with one hand, so that half or part of the cube is frozen while the other one is rotating. And if we are smart enough, right, with a finite number of combinations of such motions, we are able to drive the Rubik cube from this random combination that you see there into a combination in which all the faces are perfectly homogeneous, meaning that we have succeeded to the goal of classification, so that every color goes into the corresponding, say, basket. And this is, a simulation that was done by Borjan Geskowski. Now he's a postdoc. He was PhD with us. He's now, he's originally from Macedonia. He's now a postdoc in MIT. And this is the video he has done in order to exhibit how, if you run optimal control on these dynamical systems that are driven by these sigmoidal activation functions a la Cybenko, you can really see computationally the success of this technology to, to build machines that are able to classify, items, right? And we see here the successful classification on the fact that purple goes to a corner, yellow goes to another corner, and then greens go to a different corner. So the goal was achieved. So let me just explain you how somehow linking these very fundamental ideas of control theory, a little bit of our understanding of dynamical systems, and the very properties of this sigmoidal nonlinearity, inspired on the Rubik cube, we can understand why control can be achieved successfully. Right? So just to fix ideas, please keep in mind that sigma is this ReLU, right? ReLU x is just x plus, is the positive part of x. It's a function that is taking 0 value to the left and then is linear, the identity to the right. So you will say, well, this is a strange nonlinearity. Yeah, normally in mechanics, you don't see that nonlinearity. I mean, it can be, but I mean, it's not the most typical one, right? So if you look to the motion of a truck or a car, you will find trigonometric nonlinearities. If you look to Navier-Stokes, you will find quadratic nonlinearity. So here, I'm not inspired, I'm not really limited to the catalog of models in mechanics. I'm just building the ODE I like to build, because my goal, I am totally free, and my unique goal is to find a map that is performing successfully, classifying objects according to color as shown in this simulation done for the simultaneous control of this dynamical system. And now, let me explain you how you do it. What was the idea of Rubik cube? You just do a finite number of constant actions. You just decide this part frozen, this part rotates, and then it rotates as much. So it's just constant actions, but are constant actions that are leaving half of the cube or part of the cube frozen, while the other one is rotating. And this is what you see happens with this ODE, because you see sigma is either 0 or linear. So what is then this ODE doing? What is this ODE doing? There are two possibilities. At time t, you are sitting at point xt. What is your velocity, which determines the future of your position? I mean, in which direction you are moving? There are two possibilities. If you are sitting on a point x, where sigma ix plus b is equal to 0, then x prime is equal to 0, and then you don't move. This is the frozen part of the Rubik cube. And if you know ax plus b is positive, then sigma is active. This is actually linear. Therefore, this is a linear ODE, and this linear ODE will evolve in the direction of the wind, and this vector W is indicated. So it's very much like in the Rubik cube. The fact that sigma is that way, this acts like a guillotine and like an equator that you can place wherever you want by choosing the parameters a and b, because after all, atx plus b is just a hyperplane. It's an equator dividing the space into two half spaces. One of them will be frozen, the one in which, you know, this value is negative will be frozen. The other one will be active. And in the one that there is motion, you can decide what is the direction of motion, the direction of the wind, by the choice of this parameter W. And then you can generate motions like this. So with these ODEs, just by choosing in a piecewise constant manner the coefficients of this ODE, W, A, and B, you can generate motions of the Euclidean space in which, for instance, the southern hemisphere is frozen and the north hemisphere is moving, and then the motion can be in any direction depending on how you choose the parameters. So now with this, you are almost done, because now you have to build a machine. A machine will be an ODE on a given time horizon, in which I will choose the coefficients in such a way that every item will be classified. You give me n items, n very large, I will have to work a lot. This is like a Rubik cube. I mean, if you give me a Rubik cube like there with many faces, I will have to work much longer than the classical, say, cubic Rubik cube. But it doesn't really matter. Regardless how big it is, if I am patient enough, I will always be able to do it. So what is the tool in math that allows us to overcome the fact that regardless how many items you have for classification, you can always succeed? It's an induction argument. So in this induction argument, I can guarantee you, the only thing I need to do is to show you that wherever the distribution of points is, I can always improve the classification by classifying one more without undoing, you know, the arrangement of those that are already classified. Of course, it will be painful if in order to classify one, I have to unclassify 10, right? Because I will not be, you know, winning anything. But what I'm claiming is that I can gain one extra item classified without undoing the work that I have done in the previous iterations. So just to show you this example, that's the configuration I would like to discuss. So we have 9 toys, 3 blue, 3 red, and 3 green, organized in the room that way. And you know, the arrangement should be that the blues will go to this upper segment, the red will be in this intermediate segment, and the green in this lower segment. If they are arranged in this segment according to colors, I'm fine. I don't need more precision than this, right? So the blues to the blue, the reds to the red, and the greens to the green. So when you look at the configuration here, you say, well, I am almost done. If I simply translate all these items to the right, I mean, you know, blues will essentially go there, reds will essentially go there, and greens will essentially go there. There is very little I have to do, except what? Except the fact that there is one blue in between the reds. If I just do some linear transport of these points, you know, the blue will end up in the red basket. So I have to work a little bit to really extract the blue from here. I have to do some small chirurgy, extract the blue from here, and put it in the upper basket over there. How can I do that? My claim is that I can do it using this dynamical system idea, right? Defining the corresponding control in 3 piecewise constant actions, right? What is the first action? You remember I said with the coefficients A and B, I am choosing the hyperplane that is dividing the space into 2. So this time I choose this horizontal hyperplane just above the blue. And then with the control W, now I determine the direction of the wind in the active part. The active part is this northern area. And then I design that the wind will push towards the right. Sorry, towards the left. After some time, the configuration will be this one. These 4 that are in the north will move to the left, and the blue will be still there, right? These other ones are frozen with the blue, they are still there. You look to this new configuration and you say, well, this is not done. The blue is still surrounded by the reds. So the second action, I stop at this time, and now I change my strategy. So this, I made a motion with the Rubik cube, now I change the strategy and I do another one. So now I decide that the cutting hyperplane will be just below the blue. And now it will be the southern hemisphere that will move to the left. When I do this, right, all these red and 3 blue greens will move to the left. And I will be in a configuration in which there is blue isolated to the right with respect to all others. And then I am almost done. I take a hyperplane, which is vertical, third action, third motion in the Rubik cube, and then I choose this vertical hyperplane just to the left of the blue. I will push up on this active hemisphere, and the blue will come with the others to here. So you see how I have built a dynamical system that was able to, you know, classify items starting from this, say, initial configuration in which classification was not perfect. In this case, I just needed the ODE with 3 piecewise constant controls. Of course, if you give me a number n of items, the control will be much more complex because the number of constant arcs I will have to choose will grow. But still, I can always say that classification can be completely achieved using these ideas of simultaneous control that I achieve for this, say, called residual neural networks or neural differential equation. Neural because the sigmoid sigma in Sivenko's paper is involved very much as the governing nonlinearity of the ODE. I can build the machines that, you know, Norbert Wiener was looking for. And this machine is this just non-autonomous neural differential equation in which the coefficients have been chosen in a piecewise constant manner, right? So to achieve the goal of classification. This is, you know, the typical paradigm of supervised learning. And then for those that are interested, of course, you can easily find also a link with, say, optimal transport, because we know that the solution of ordinary differential equations are the characteristics lines for hyperbolic first order transport partial differential equations, right? And in some sense, when we are, you know, classifying items, is like designing the characteristics. This is precisely the kind of work you do when you are dealing with the challenges of optimal transport, except that in here, the transport is not done optimally, but the transport has the specific feature of being done through a neural, say, vector field. Okay, so this is just a very small explanation of how a number of relevant results in machine learning can be understood from the perspective of control. Once you do that, then you can bring all the know-how of control into machine learning to enrich, you know, your understanding of machine learning. And also, I think, and I hope this helps to the others, once you see this bridge between, say, control or more classical, say, applied mathematics, dynamical systems, numerics, and so on, together with machine learning, when you see one of these bridges built, you can probably more easily figure out how you do it from your own know-how, your own area of expertise. Thank you for your attention.